Everything we see, everything we know, and even we ourselves, all began from a single point. It's a mind-boggling thought, isn't it? But all the evidence suggests that our universe, in all its vastness and complexity, started as something incredibly small and hot. It was smaller than a grain of sand, yet it contained all the energy and all the matter that would ever exist. This moment, which happened around 13.8 billion years ago, is what we call the Big Bang. It wasn't an explosion in space, like a firework. It was the moment space itself began to expand, and it has been expanding ever since. It was the beginning of time itself. In the first fractions of a second after the Big Bang, the universe was a swirling, searingly hot soup of pure energy. As it expanded, it started to cool down, and this cooling allowed something truly remarkable to happen. Energy started to transform into tiny particles, the fundamental building blocks of everything. These particles then began to clump together to form the very first atoms. The conditions were just right for the simplest and lightest elements to form. These were hydrogen and a little bit of helium. For millions of years, the universe was just a vast, dark cloud of these two gases, with nothing else to see. Imagine a universe filled with just a dark, swirling fog of hydrogen and helium. There were no stars, no planets, no galaxies. It was a simple, almost empty place. But within these enormous clouds, gravity was quietly at work. Gravity is the force that pulls things together. It might seem weak, but over immense stretches of time, it is incredibly powerful. Slowly, patiently, gravity began to pull the clouds of gas into denser and denser clumps. These clumps were the seeds from which the first stars and galaxies would eventually grow. The universe was getting ready for its next great act, the creation of light. So, this was the dawn of our cosmos. A universe born from a single point, expanding and cooling, and then populating itself with the simplest atoms. It was a dark and quiet place for a very long time, but the stage was being set. The hydrogen and helium formed in these first few minutes are still the most abundant elements in the universe today. They are the raw materials from which everything else would be made. The story of our planet and of us starts right here, in this ancient, simple universe, waiting for the first stars to ignite and change everything. For hundreds of millions of years, the universe remained dark. The vast clouds of hydrogen and helium drifted through space, but gravity was relentlessly pulling them together. In the densest parts of these clouds, the gas became so tightly packed that something spectacular happened. The pressure and temperature at the center of these clumps grew to unimaginable levels. It became so hot that the hydrogen atoms began to fuse together, creating helium and releasing a tremendous amount of energy in the process. This burst of energy was the birth of the very first stars. The universe was no longer dark. It was filled with light. These first stars were giants, hundreds of times more massive than our own sun. Because they were so big, they burned through their fuel incredibly quickly, living for only a few million years. Inside their fiery cores, they were like cosmic factories. The intense heat and pressure forced atoms to smash together and create new, heavier elements. They turned hydrogen and helium into carbon, nitrogen, and oxygen. These are the elements that are essential for life as we know it. Without these giant, short-lived stars, the building blocks for planets and people would never have been created. They were the universe's first great chemists. When these massive stars reached the end of their lives, they didn't just fade away. They went out with a bang in some of the most violent events in the universe, supernovae. A supernova is a colossal explosion that can briefly outshine an entire galaxy. This explosion blasted all those newly created heavy elements out into space. The carbon from a star's core, the oxygen, the nitrogen, all of it was scattered across the cosmos like seeds on the wind. These elements mixed with the existing clouds of hydrogen and helium, enriching them with the raw materials needed for the next generation of stars and planets. So, you see, the universe is a grand cycle of creation and destruction. The death of one star provides the material for the birth of another. Each generation of stars creates heavier and heavier elements, from the iron in your blood to the calcium in your bones. All of these elements were forged in the hearts of stars that lived and died long before our sun was even born. We are, in a very real sense, made of stardust. The atoms that make up our bodies, our planet, and everything we see around us have been on an incredible journey through space and time, all starting in the furnaces of these ancient stars. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, our own story began. A vast, spinning cloud of gas and dust, enriched by the explosions of long-dead stars, started to collapse under its own gravity. This cloud, called a solar nebula, was enormous, spanning light years across. It contained all the ingredients needed to build a solar system: the original hydrogen and helium from the Big Bang, and all the heavier elements like carbon, oxygen, silicon, and iron that had been forged in stars. As the cloud spun, it began to flatten out, just like a ball of pizza dough when you spin it in the air. Most of the material in the collapsing nebula spiraled towards the center. The pressure and density there became immense. As more and more gas and dust piled up, the temperature at the core soared to millions of degrees Celsius. Eventually, it became hot enough for nuclear fusion to begin. Hydrogen atoms started fusing together to form helium, releasing an incredible amount of energy. At that moment, a new star was born, our Sun. It lit up, and its powerful solar wind, a stream of charged particles, blew away much of the leftover gas and dust from the immediate vicinity, illuminating the young solar system for the first time. The material that wasn't pulled into the Sun didn't just disappear. It formed a vast, flat, spinning disk around the young star. This is called a protoplanetary disk. Think of it like a giant cosmic frisbee made of gas, dust, ice, and tiny rock fragments. Within this disk, temperatures varied greatly. Close to the hot new sun, it was too warm for anything but rock and metal to exist as solids. Further out, in the colder regions of the disk, it was cool enough for water, methane, and ammonia to freeze into tiny ice particles. This difference in temperature is the key to understanding why our solar system has different types of planets. This spinning disk was the birthplace of the planets, including our own Earth. It was a chaotic and busy place, with countless tiny particles all orbiting the young sun. Over millions of years, these small particles would begin to stick together, growing larger and larger in a process that would eventually build entire worlds. The sun, the glowing heart of our solar system, had been born, and the stage was now set for the formation of its planetary family. The journey of Earth was about to begin, starting as just another collection of dust and rock in this vast, swirling disk. Within the swirling protoplanetary disk surrounding the young sun, the process of planet formation was underway. It started small. Tiny grains of dust, no bigger than particles of smoke, began to stick together. This process, called accretion, was a bit like how dust bunnies form under your bed. Static electricity might have helped the first grains clump together, but as they grew larger, their own gravity started to take over. These small clumps of dust and rock, growing from centimeters to meters in size, were the first seeds of the planets. They were floating through the disk, colliding and merging. Over thousands of years, these clumps continued to grow. They smashed into each other, sometimes shattering, but often sticking together to form even bigger objects. These objects, now kilometer-sized, are called planetesimals. You can think of them as mini-planets. Our early solar system was a cosmic demolition derby, filled with trillions of these planetesimals, all zipping around and crashing into one another. The inner solar system, where it was hot, was dominated by rocky and metallic planetesimals. This is the region where Earth and the other rocky planets, Mercury, Venus, and Mars, would form. As the planetesimals grew larger, their gravitational pull became stronger. The biggest ones started to dominate their orbits, pulling in smaller planetesimals and clearing a path through the disk. These growing giants are called protoplanets. The early Earth was one of these protoplanets, a growing ball of rock and metal constantly being bombarded by smaller bodies. Each collision added more mass and, crucially, more heat. The energy from these constant impacts was enormous, and it played a vital role in shaping the young planet that was taking form. Our world was being built, one violent collision at a time. This chaotic process of accretion continued for millions of years. Eventually, the protoplanet that would become Earth grew to be the largest object in its orbital path. It had swept up most of the debris and planetesimals in its neighborhood, growing to roughly its current size. But it was not the calm blue world we know today. It was a hostile and violent place, a sphere of molten rock still glowing from the heat of its formation. The journey from a speck of dust to a full-sized planet was complete, but the story of Earth was only just beginning. The newborn Earth was a truly hellish place. It was nothing like the world we live on today. The constant bombardment by planetesimals and asteroids during its formation had generated an incredible amount of heat. Each impact was like a massive explosion, releasing enormous energy that melted rock and kept the surface of the young planet in a molten state. Imagine, for a moment, a whole world covered not by oceans of water, but by a global ocean of bubbling, glowing lava. The temperature on the surface would have been thousands of degrees Celsius, hot enough to melt any rock. But, this intense heat didn't just come from collisions. Another major source of heat was radioactivity. The dust and rock that formed the Earth contained unstable elements like uranium and thorium. As these elements decayed over millions of years, they released a steady stream of energy, much like a slow-burning nuclear reactor. This internal heating added to the heat from the impacts, ensuring that the entire planet was molten, right to its very center. This early, fiery phase was a crucial step in Earth's development, as it allowed the planet's materials to move around and sort themselves out. A third source of heat came from the immense pressure at the planet's center. As Earth grew larger, the force of gravity pulled all its material inwards, squeezing the core with unimaginable force. This compression generated yet more heat, contributing to the planet's molten state. So, you had a triple whammy of heating constant impacts from space, radioactive decay from within, and intense pressure from gravity. It's no wonder that the early Earth was a glowing ball of liquid rock, a far cry from the solid ground we stand on today. This period, known as the Hadean Eon, is named after Hades, the underworld of Greek mythology, and for good reason. It was a world of fire and chaos. There was no solid surface, no oceans of water, and no breathable atmosphere. Any water that arrived on comets or asteroids would have instantly boiled away into space. The sky would have been a murky reddish haze, choked with dust and volcanic gases. It was a planet still in the process of being born, a violent and inhospitable world waiting for the long, slow process of cooling to begin. As the bombardment from space began to slow down, the Earth finally had a chance to start cooling. The heat from its surface began to radiate away into the coldness of space. This cooling process was very slow, taking millions of years, but it allowed for one of the most important events in our planet's history to occur: differentiation. While the Earth was still a molten ball, the heavier materials were free to sink towards the center, while the lighter materials floated towards the surface. It was like a giant cosmic salad dressing separating into layers. The heaviest elements, mostly iron and nickel, sank right down to form the planet's core. This created a dense metallic center for our world. The core itself separated into two parts: a solid inner core, squeezed solid by immense pressure, and a liquid outer core surrounding it. The movement of the liquid iron in this outer core is incredibly important. As it sloshes and churns, it generates a powerful magnetic field that extends far out into space. This magnetic field acts like an invisible shield, protecting our planet from the harmful solar wind and cosmic radiation, which would otherwise strip away our atmosphere. Above the core, the lighter, rocky materials formed a thick layer called the mantle. The mantle is not quite solid and not quite liquid. It's a bit like very, very thick treacle that flows incredibly slowly over millions of years. It makes up the vast majority of Earth's volume. Finally, as the very top layer of the planet cooled and solidified, it formed a thin, brittle shell of rock on the surface. We call this the crust. It's the part of the Earth we live on, the ground beneath our feet. Compared to the mantle and the core, the crust is incredibly thin, like the skin on an apple. So through this process of cooling and differentiation, our planet transformed from a uniform ball of molten rock into a structured world with distinct layers: a dense metallic core, a vast rocky mantle, and a thin solid crust. This separation was fundamental to everything that came next. The formation of the magnetic field protected the future atmosphere, and the creation of a solid crust provided a surface where oceans could one day form and life could eventually take hold. The fiery, chaotic Earth was beginning to look a little more familiar. Our planet has a large and beautiful companion in the sky, the Moon. But where did it come from? For a long time, this was a great mystery. The leading theory today is called the giant impact hypothesis, and it describes a truly cataclysmic event in our planet's early history. According to this idea, soon after the Earth had formed and developed its layers, it wasn't alone in its orbit. Another protoplanet, about the size of Mars, was on a collision course with our young world. Scientists have given this rogue planet a name, Theia. The collision was unimaginably violent, the biggest crash our planet has ever experienced. Theia struck the young Earth at a glancing angle, not head-on. The impact was so powerful that it completely melted the Earth's outer layers and blasted a colossal amount of vaporized rock and debris into orbit. Theia itself was obliterated in the process. For a short time, the Earth would have been surrounded by a glowing ring of molten rock and gas, similar to the rings of Saturn, but much hotter and more massive. It must have been an incredible sight. This ring of debris didn't stay a ring for long. Gravity quickly went to work, pulling the material together. Over a surprisingly short period of time, perhaps only a few thousand years, the debris clumped together to form a single, large body, the Moon. At first, the Moon was much closer to the Earth than it is today, appearing huge in the sky. It was also a molten ball of rock, just like the Earth, glowing from its own heat. Over billions of years, it has slowly cooled and gradually moved further away from us, a process that continues even today. This theory explains many strange things about the Moon. For example, moon rocks brought back by the Apollo astronauts are very similar in composition to rocks from the Earth's mantle, but they lack the heavy iron we find in Earth's core. This makes sense if the Moon formed mostly from the outer layers of Earth and Theia. The theory also explains the Moon's small core and why its orbit is tilted. The giant impact was a chaotic and destructive event, but from it, the Earth gained its constant companion, a satellite that stabilizes our planet's tilt and gives us the rhythm of the tides. After the Earth cooled enough to form a solid crust, it was still a dry and airless world. The next crucial ingredients for life, water and an atmosphere, had to come from somewhere. For a long time, the planet's surface was a landscape of dark volcanic rock. And it was these volcanoes that played a key role. As the rock in the mantle churned and melted, it released trapped gases. These gases, including water vapor, carbon dioxide, and nitrogen, erupted from thousands of volcanoes all over the planet's surface in a process called outgassing. This volcanic outgassing slowly began to build up Earth's first proper atmosphere. It was not an atmosphere we could breathe. It was thick with carbon dioxide and steam with almost no oxygen, but it was a start. As the planet continued to cool, a critical point was reached. The temperature of the atmosphere dropped low enough for the water vapor to condense into liquid water. It began to rain. And it didn't just rain for a day or a week. It may have rained for centuries, a relentless global downpour from the steamy skies. This great rain filled up the lowest-lying areas of the Earth's crust, the vast basins that had been formed by ancient impacts and volcanic activity. Slowly but surely, the first oceans were born. But volcanoes weren't the only source of water. During this early period, the Earth was still being hit by objects from space, though not as frequently as before. Many of these objects were comets, which are essentially giant dirty snowballs made of ice and rock. Asteroids also contain water locked within their minerals. Every comet and water-rich asteroid that crashed into Earth delivered a fresh supply of water, helping to fill the growing oceans. So our planet's water and air came from two places, from within, through volcanoes, and from above, through comets and asteroids. This created a world with a thick, carbon dioxide-rich atmosphere and vast global oceans. It was still a harsh environment with a weak young sun and no protective ozone layer. But the arrival of liquid water was the single most important step towards making Earth a habitable planet. Water is the solvent for life, the medium in which the chemistry that leads to living things can happen. The stage was now set for life's mysterious origin. With oceans of water covering a warm, rocky planet, Earth had all the basic ingredients for life. But how did non-living chemicals come together to form the first living organisms? This is one of the biggest questions in science, and we don't have all the answers yet. But we have some fascinating ideas. The early oceans were a rich soup of simple chemicals. The atmosphere had carbon dioxide and nitrogen, and the water contained minerals dissolved from rocks. Energy was also plentiful, coming from lightning strikes, volcanic heat, and powerful ultraviolet radiation from the sun. In the 1950s, an experiment called the Miller-Urey experiment tried to recreate these early Earth conditions in a laboratory. They mixed together water, methane, ammonia, and hydrogen, gases they thought were in the early atmosphere, and zapped them with electric sparks to simulate lightning. After just a week, they found that complex organic molecules had formed, including amino acids, which are the building blocks of proteins. This showed that the basic chemical components of life could have formed naturally on the early Earth. Life's ingredients were not hard to make. So where might life have actually started? One popular idea is that it began in shallow sunlit pools of water, often called warm little ponds. Here, the chemicals could become concentrated as water evaporated, and energy from the sun could power chemical reactions. Another very compelling location is deep beneath the ocean, at hydrothermal vents. These are cracks in the seafloor where hot, mineral-rich water from the Earth's interior gushes out. These vents are like chemical factories, rich in energy and protected from the harsh radiation at the surface. They could have been perfect nurseries for the first life. Whatever the location, the first life was likely very simple. Probably just a single cell. It would have been a microbe, far too small to see. For billions of years, these simple organisms were the only form of life on Earth. They slowly changed the planet, with some learning to use sunlight for energy in a process called photosynthesis. This process released oxygen as a waste product, and over an immense timescale, this oxygen built up in the atmosphere, transforming our planet and paving the way for the more complex life we see today. From a simple chemical soup, life had taken root and begun its incredible journey of evolution.